Hello, my name is YunSeok Choi. I am a student at Sungkyunkwan University. Today the paper I will introduce is embedding method for unseen words, considering contextual information and morphological information. The order to introduce is as follows: introduction, related work, and proposed method, experiment, and conclusion. Word embedding is a vector representation of a text word. General embedding is word-to-back. Word-to-back is learned with a neural network model when a vector is mapped to a lower latent space vector. Then similar words are mapped to similar latent space. Another word embedding is to be learned using a language model that predicts the next word. For learning word embedding, we prepare corpus data and we make word embedding table. For example, there are blockchain technology important in vocabulary table. Then, LSTM model is used to learn word embedding to predict the next word. For example, input sentence is blockchain technology is important, and the model is learned to predict the technology word. Here, the input word is mapped to the index, and embedding layer translates the index to word vector. Finally, the word embedding is learned to predict the next word. But not all words are in the vocabulary table. Out of vocabulary is words that is not in the vocabulary table. Here, captain does not exist in the vocabulary table. How do we assign a word embedding value to captain Q? When we assign our vocabulary to word embedding, we need to assign the embedding using morphological information and textual information. In previous work, to solve our vocabulary problem, word embedding is calculated in character unit. The author proposed the CNN model to embed the word. The convolution kernel size is different in n-gram units and embedding in n-gram units is calculated. Finally, one word embedding is calculated by concatenating n-gram embeddings. This model used morphological information, but they did not consider the contextual information between word and word. Also, recently, transformer model was proposed for a language model. This model learned the word embedding using word-to-word self-attention, so the model considered contextual information. But the word embedding was learned in word unit, so morphological information was not considered. So we proposed a model concatenating character CNN and transformer model for contextual information and morphological information. So we proposed a model to solve out of vocabulary using contextual and morphological information. This figure is the training architecture. This training architecture is called replace token detection task. Replace token detection task was proposed in Electra model. This learning process consists of generator and discriminator. When a sentence is an input, we tokenize the sentence as token level, and 15% of words are randomly replaced into mask tokens. Generator is learned to predict what word the mask token, and we aggregate tokenized words into word level words, and discriminator is learned to predict whether the generator of sentence are replaced or original compared to original sentence. And this is the structure of a replace token detection task. And this architecture is generator and discriminator. Generator model is general transformer encoder model, and discriminator model is our proposed model. context character transformer encoder. The difference between context character transformer encoder and traditional transformer encoder is characterization and embeddings. In order to process our vocabulary words effectively, we propose a model that represents words by combining words, morphological information, and contextual information. We use a character level CNN for extracting words, morphological information, and we use transformer model for extracting words, contextual information. For example, if there is a sentence, I like apple juice, and one word embedding is obtained with character CNN for each word, and another word embedding is obtained by using the transformer model for one sentence. Finally, by adding a module called the context character gate, a proper combination of word contextual information and morphological information is provided. Here, this is the pseudocode and model architecture of contextual character transformer encoder. The red box calculates word embedding using character CNN to obtain the morphological information of the word. Then, in the blue box, it is learned using multi-head attention for the contextual information between words. And in the green box, in order to transform word embedding containing morphological information, we use a feed-forward layers. And in purple box, using the context character gate, the word embedding that combines the contextual information and morphological information is calculated. This is our proposed model hyperparameter. Hidden state dimension is 512 and number of layer is 6. Number of attention head is 8. To evaluate performance of our model, we conducted experiments on the CoNL 2003 dataset. We also artificially created two variants of the CoNL 2003 dataset to evaluate performance of OOV words. Shuffle data is the variation of the original data, which shuffles the intermediate character order of dataset. For example, recommend RECOMMEND is replaced to RECOMMEND. This is to evaluate whether the model is robust to a type of OOV words. A mixed dataset is the variation of the original data, which replaces the word to the mixture of two words. Mixed words can be compound words that become a different meaning by combining two words. For comparison, we manually implemented all the models for evaluating the performance on the same environmental settings. All the models, except for BERT, we add two layer by LSTM layers above the pre-trained embedding layer and use the Adam optimizer with same learning rate using linear decay for fine-tuning. And BERT model is more bigger than our proposed model, 12 layers, 12 multi-heads, and 768 dimensional embedding. This table represents the result of name entity recognition and part of speech tagging task for CoNL 2003. Original data refers to the original data, and shuffled contains 60% of words which generated by shuffling, and mixed to replace the words corresponding to location name with the mixture of two words. Experiments on name entity recognition tasks for shuffled and mixed dataset show that the proposed model has the best performance. In an experiment on name entity recognition, task for original dataset shows that BERT has the highest performance. But the proposed method with a relatively similar model show that the performance of the proposed model is higher than that of other embedding technique. In addition, for shuffled and mixed data with more OB words than the original data, the proposed model shows a lower performance driven rate than BERT, which show robustness to compound words not seen during training. In the post-tagging experiment, the proposed method and the BERT show the best performance for all data, although the performance of the two models is almost the same, but the proposed model has strength in model size. And these tables present the result of name entity recognition task for other three datasets. The best performance is in bold type, and the second is underlined type. The proposed method for all datasets shows the best performance. Experiment on MMC dataset, the best model and the next best model show the same performance. On NUTOT dataset, there is a little performance margin, and WNUT17 dataset, there is a large margin between the best and the second model. This table shows statistics of sentence length by word level and word piece level, or of a null task dataset. As MMC, NUTOT, WNUT, the ratio of word and word piece increase. A higher ratio means that more words are split, which means there is a lot of unseen word. Therefore, showing superior performance when the ratio is higher means that better on processing unseen words. In this experiment, this table shows the result of calculating cosine similarity for OB words to verify whether they are reasonably embedded in OB words by embedding method. OB refers to a sentence containing OB words, and IN1 to a sentence containing a dictionary with a similar meaning to an OB words, and IN2 is a sentence containing a dictionary with a similar spelling to an OB words but completely different meanings. The number in the table are the similarity between OB by IN1 and OB by IN2. From a human perspective, OB by IN1 similarity should be higher than OB by IN2 similarity. Table shows that fast text allocate almost random values for OB words, so their cosine similarities are low, while there is a little difference between OB by IN1 and OB IN2 in the case of BERT. The proposed model shows that the OB by IN1 similarities are generally higher than OB by IN2. In this result, the proposed method showed that the morphological information and contextual information of the words properly process OB words that were not seen when the model is trained. In conclusion, we propose the context character transformer encoder using contextual and morphological information to process the misrepresentation problem with OB words. Experiments showed that the proposed model, which is smaller than the existing pre-trained models, generally outperforms. And especially when there are more ovoids, the proposed model shows superior performance with a large margin, and cosine similarities comparisons of word pairs show that the proposed model properly considers morphological and contextual information. Thank you.